holding for start. Okay, in this video, what I'd like to show you then is how is it that you can use Pavre for Windows or Megapav for Macintosh and the so-called skeleton code, which you can find online for free, to start generating physics videos. How is it that you can start getting objects to move around and play around and simulate with physics? Well, that's what I'm going to show you here. So the first thing you need to do then is load your Pavre or Megapav up and load up the skeleton code. Let me give you a quick tour of the skeleton code, then we'll get into actually making some animations. So the first thing about the skeleton code is there's always going to be a line at the very top called include physics.inc. Now, physics.inc is not something you need to worry about. It's sort of some pre-written routines, which you can also find online to download, sort of where you found all this other information here. And it includes just a bunch of drawing routines that will pop up in physics, like say drawing vectors or drawing a spring or drawing an energy bar or something like that. That's all going to be found in physics.inc. And what's in physics.inc you can find in the book, which is also posted online, you can get, but just leave it in there. The next thing you need to do sort of has to do with ray tracing, is that whenever you do ray tracing, you also have to specify where the camera is going to be that films what happens in your scene and where the light source is going to be, which illuminates your scene. So as you can see here, I have a camera statement that Pavre and Megapav both recognize. In order to say where the camera exists, I use the location directive here, and I tell it I want to be at 0, 0, minus 15. Now these directives here that start with a less than sign and a 0, 0, minus 15 are something you have to get used to as you use this system for animation. It refers to a full vector. The very first component is always the x, the second component is always the y, and the last component is always the z. So what I'm saying here is I want a camera whose location is at 0, 0, minus 15. X of 0, y is 0, z is minus 15. Now that minus 15 is the z-axis, and that's the one that sort of extends out towards you. So if you imagine a line stuck in the center of your screen, a line that comes out of your screen, through your nose, through your head, out the back of your head, that would be the minus z-axis. So by putting a minus 15 in here, I'm telling it that I want the camera of my scene to be approximately where my face is, I would say, as the computer's being used. So that's where it's setting the camera, that's where it's placing the camera. But just because the camera's placed, now it needs to be aimed, and that's what the look at statement does. So I can aim the camera anywhere I want, but I'm choosing with this look at directive here to aim it right at the origin, 0, 0, 0. That's usually where my action is. And so notice once again is I have x of 0, y of 0, and z of 0. Once again, all in that sort of that vector directive with a greater than and less than sign, the brackets. You'll also find this notation in calculus text and some physics text say, okay? So the camera's set. It's going to be at 0, 0, minus 15, looking straight at the origin. Next, I need to illuminate the scene, and I use that with my light source directive. So the light source here is going to also needs to be placed somewhere, like where do I want the light source to be in my scene? And so I'm choosing to place it just behind the camera. So if the camera's at 0, 0, minus 15, I'm putting the light source at 0, 0, minus 20. So it's back behind my head a little bit, and I'll make it a white light source to illuminate my scene with white. So with the camera and the light source all set up, you're sort of ready to get going now. That's required of ray tracing, and so off we go. We have a camera and a light source. Next, we'll start getting into a bit of physics. This line here, so first of all, in Pavre and Megapav, whenever you set up a variable, you always need to put a pound declare in front of it to get things going. It's just part of the syntax of the language. But in either case, I have a variable called pose here. Now, pose is short for position, and I'm telling it that I want an object here whose position is at 0, 0, 0. So once again, you see that three-dimensional vector notation right here. If I get it and even retype this just for emphasis here, I want x of 0, y of 0, and z of 0. Close bracket, and I always need a semicolon after a pound declare statement. I'm putting an object at 0, 0, 0, x of 0, y of 0, z of 0. In the very next line, I'm declaring another variable, which is vel, short for velocity. And I also want that to have no components initially starting out. So I want 0 velocity in the x direction, 0 velocity in the y direction, and 0 velocity in the z direction, like that. That's what vel. So see, I'm starting out to get into physics already, early stage here, by declaring two variables, pose and vel. Position at 0, 0, 0, velocity 0, 0, 0, no components of velocity in either direction, or 0 components in all directions, either way you want to think about it. So that's pose and vel, position and velocity of the object I'm about to start animating. Next, I have something called dt, which stands for delta t. That's how much time I want to go by between my frames. A dt of 0.1 seems to work best for most of what we'll do. Certainly, smaller dt's give you very fine resolution motion, highlights all the details and very smooth motion, whereas larger DTs can give you very jumpy motion. You have to be very careful of it because sometimes large DTs cause you to miss features or things behave sort of erratically. So as I said, a DT of 0.01 works well for most cases here. Next, I need to keep track of the overall time that happens in the movie. This variable called x time often won't affect you. I would have liked to call it time, but time is used internally by Pavre and Megapav, so I couldn't, so I just threw an x in front of it. But if you imagine somewhere, just an imaginary clock exists inside your movie somewhere, keeping track of how much time has gone by, that's what X time holds for it. So we'll just leave it there. Okay. Next, there's something called a while loop. We're not going to belabor what a while loop does here. You can look that up in Wikipedia, or maybe you know for some other programming experience. But the only thing you need to know is this while loop always has to be here, and it's paired with this end statement down here, which also always has to be there. And this sets up a core while loop for the program to sort of get things going here. So there's a while loop here. I'm going to ignore that for now, and maybe just forever. But what I want to do next is notice that I'm declaring an acceleration now. So see, the physics is deeply intertwined in what we're doing here. Up here is a position. Here's a velocity. Well, now I'm getting into acceleration. So I've got an object at the origin, 0, 0, 0, with no velocity, and also doesn't have any acceleration. So you can see we're setting ourselves up for a fairly boring animation here, something in the center of the screen with no velocity, no acceleration will never move, but you'll have to agree with me, you're already addressing some ideas of physics in there, because indeed, something with no velocity, no acceleration will never move, and you can even simulate that here. The very next thing we see in our code is what you'll just find in the early chapters of your textbook. Physics equations. This is pose plus vel dt plus a half a dt squared. If you look very carefully in your physics book, you'll find some equations say x equals x0 plus v0 delta t plus 1/2 a delta t squared. This is one of the first and most rudimentary kinematic equations there exist in your physics book, and we're going to use it here. This is the one that says, hey, if I know where my object is, what its speed is, and what its acceleration is, and I have some time step, put all those together, this physics equation will tell us the new position of the object, the new pose. That's like the x. I also have the same thing for velocity down here. It says, hey, this equation says if I know the current velocity of my object and its acceleration and some time step, I will tell you the new velocity of the object. There's the bell. So see, already in this skeleton code, the physics is deeply intertwined. I have two physics equations all ready to go in there. Next, I have a sphere drawing statement. This directive tells Power to draw a sphere. In this case, it will be a yellow sphere. The center of the sphere will be at POS, or the position of my object here, and the radius will be about 0.1, so it'll be fairly small. Turns out this sphere here will draw the breadcrumb behind an object that moves, and I'll come back to that in just a second. But for now, just keep that in mind. And last, I need to update my internal movie clock. I won't worry too much about this line. Now, if I look after the end statement, this end statement, of course, is paired with the while, as I mentioned above. If I look below it, this is where I do any final drawing of my scene. So see, I have another sphere drawing statement here where I want to draw a sphere, again, at the position that was returned by my physics equation. I want to make it red, and I want to give it a radius of 0.5. You can choose whatever radius you want. 1, 2, 3s are getting kind of big, so I chose 0.5. So if I just run this thing now, let's just go ahead and render. I'll talk about these two statements in just a second. Let's just get some visuals up we can look at. I'm just going to hit the render button now. And before I do that, make sure, at least if you're on the Macintosh, and I'll tell you some Windows hints in a second here, that you have this animation settings check mark on here under clock settings. And also you've chosen some number of frames that you want to animate. In this case, I've got a 30 here and a 30 down here. So make sure these numbers in these lower two boxes are always the same, and go ahead and turn that on. If you're using Windows, there's a big white type-in box just above your edit screen, which you would type final underbar frame equals a 30, and that's all you need to do in Windows. Check the book, it'll tell you how to get all that going. In either case, let's hit render now, and off we go. So see, I see some graphics appearing here, which is a red sphere, and nothing much seems to be happening. That's what we said. We set ourselves up for a pretty boring video, but we are investigating physics. Something with no velocity, no acceleration would just sit there forever. How would I get that to move? Well, I can just go up here to my velocity statement. Instead of giving it no velocity on all axis, give it a little velocity along the x-axis. Give it a +5 along the x-axis. And now before I render it, we will get some motion now, but let me drop down here and cover these last two lines here, which are our draw vector statements. What these draw vector statements do is they'll actually draw the vectors on the object itself. And let me tell you how that works. Draw vector is a function which is built into physics.inc. It's something that's in that include file you put up here. In either case, what draw vector does, it says, draw me a vector, but for a vector, because it's an arrow, I need to know where the tail of the vector is and what vector to draw. So the very first parameter is where the tail of the vector should go. In this case, I'm just choosing POS. So in other words, I want the beginning or the tail of my vector to be right at the center of the object. So if I'm drawing my object at position POS, that's where I want the tail of my vector to be as well. So I'm telling you to draw the vector with the tail right at POS, and the vector I want to draw is the vel, or the velocity vector. Go ahead and draw that vector in green and give it a label V. And just to be complete, because we're studying physics here, using the exact same sequence here, even at pose, I'll draw the acceleration vector. There's the A right there in blue with the text of A on there. So once again, let's render it, keeping in mind that I changed the x velocity up here to 5 instead of 0, what it was before, which is what it was before. So off we go. So we see we're going to get a little motion now. There goes the object off to the right with its 5 units of velocity in the direct x direction, something like that. Now, I told you before I'd come back to what those little yellow spheres are, the breadcrumbs. Let me go ahead and stop this here. If I go back to the breadcrumbs here, and this is a line that's drawing the breadcrumbs or the trail behind the object. If I get rid of the line, or alternatively, instead of getting rid of it, let me put 2 slashes in front of it like that. Now, 2 slashes in POV and MegaPOV stands for a comment. Anything after the 2 slashes are ignored. So even though I have a valid programming statement here, it's going to be ignored because of the 2 slashes. And if I run the rendering again, notice that the yellow trail behind the object are gone. So indeed, this sphere drawing statement is responsible for drawing whatever trail I might like behind an object. So I'll go ahead and turn that back on because I kind of like it. It's useful to visualize what the motion is going to look like. And so we can sort of go back then. There's my V going out that way. If I want to start playing around with physics a bit, I can launch things to the left by testing myself on minus signs. Put a -5 right there for velocity in the x direction, not a positive. Suddenly the object starts moving towards the left. There it goes. And I can keep it moving towards the left like that. And suppose then I left that, and instead of just having it keep moving to the left, suppose I put a little acceleration on it, maybe 3 units of acceleration towards the right. So I have a case here, an object that's going to be moving to the left initially, but has an acceleration to the right. And I go ahead and run that. And I hope you can start to see how the physics is wrapped into this computer animation, because you are totally going over the meanings of position, velocity, and acceleration insofar as how basic mechanics works here. So you've set up a simulation here where you're launching an object towards the left, but you have an acceleration towards the right. There's an entire lesson in your physics textbooks about how this type of motion works, in particular when V and A have opposite signs. It's a case where something slows down. So indeed, you see as this object moves here, you see the velocity vector getting smaller and smaller and smaller as it moves. It'll eventually become 0 and turn itself around and just follow this acceleration vector here. So see, there's my trail being drawn there. You can just barely make out some of the little yellow dots in there. They're being obscured by the blue acceleration vector. But I see some very relevant physics going on in here, that here's my velocity actually being turned around by this acceleration. Now, I've only have 30 frames to render. I'm already at 20, so I have 10 more frames to go. But you can see you're definitely experimenting with physics and the skeleton code. You can put an object to rest and keep it at rest, or you can start giving it velocities and accelerations to your heart's content, and just start watching what subsequent motion you'll get out of it. So let me go ahead and stop this thing here. Just a few more runs here. I'll go ahead and set the acceleration back to 0. Suppose I ventured on some other coordinate right here, so instead of putting 0 in the y direction, or the non-zero component in the y direction, in the x direction, suppose I put it in the y direction, so 5 units in the y direction and render it. Then you see I'm going to get my object to start moving straight up. So you can do something like a free fall if you want. You can launch an object straight up like that. And if I came down here to my acceleration and made the y acceleration, notice not the x or the z, but the y, minus 9.8 for the acceleration due to gravity, then I have a nice free fall animation going there. There's my 9.8. It's going to be kind of big. Looks like it's going off the screen and stuff. But I see my velocity vector rapidly becoming 0 as it goes into free fall, and it'll turn back around and follow that acceleration vector. You can just barely see the tip of the acceleration vector sticking out there. If you don't like the size of the vectors, like they go off the screen the way they're doing, there's a couple things you can do. You can back up some more. Instead of being at minus 15, maybe you can go back to minus 25 or something like that, so you can see the whole scene a little bit better. But if you're still not too pleased, it looks like the vectors are a little bit large here. What you can do is go down here to just before your first draw vector. You can do something like set vector scale 0.5. Set vector scale is another function in physics.inc that allows you to set the overall scaling of your vector. So by putting a 0.5 in there, I'm telling it to cut all vectors down in length by a factor of 1/2 when it runs it. So if I render it again, there's all my vectors a bit smaller now, so I can totally visualize the acceleration and the velocity vectors sort of as it goes. So this is an object that's thrown up, but gravity is persistently pulling it back down again. So off it goes. But I hope you can see there's just tons of experimentation you can do with basic motion in the x, y, and even the z coordinates, all you want here. And so that's a free fall case here. And there's no reason to just restrict the velocity just to the x or y axis. I can certainly give it 5 units in the x and y positions, and the z for that matter. Maybe I'll launch it towards myself just a tad bit. I'll leave that downwards acceleration. I'll just see what it gets. But here we go. So here's an object which sort of launched diagonally, a bit towards me, a bit up, and a bit to the right. And you can see it's almost like a 3-dimensional projectile being launched, but it's going to start making that nice parabola, which was characteristic of this type of motion. And off it goes. Just a beautiful example of well, computer animation. So we're going to let this run as we wrap up with a few closing comments here. Hopefully you've got your POV Ray MegaPOV ready to go. You've got your animation settings turned on here, a few frames, up to 30 or 50 usually works. And then if you go back in your source code and you just start selecting positions, velocities, and accelerations of your object, you've got these physics equations here in there which will happily project predict the trajectory your resulting object will have. And it's just a wonderful way of tying some of the basic kinematic ideas in a physics textbook with some actual animation on the computer screen. So good luck, have fun with it. It's quite fun to play around with.